everyone. We're getting started a tiny bit later than usual tonight. Sorry about that. It sounds like the audio is working good. All right. So hopefully everyone is doing great on the exam. I figured I probably wouldn't have any live viewers tonight since it is the exam is still out and people are still working on that. However, I'm gonna have a little bit of a unusual recording week in terms of when I do it for people who like to watch ahead of time. So tonight I am gonna keep recording. I won't push it back just because the exam's out, because my wife will be at a bachelorette party on Thursday and Friday, and I won't be able to record as usual. So I'll do Monday, Tuesday, Wednesday instead of the usual Monday, Wednesday, Friday this week. Tuesday might be at a weird hour. We'll see. But I'll post it all like normal. So it's 3 lectures, same as normal, just slightly different days. So I can't waste today, since even though people are still working on stuff and all that, just watch it whenever you want. I figure most people will anyway. Hopefully the exam is going pretty well. If you are stuck on any questions, if you're stumped, just let me know. Shoot me an email and I can maybe give you a hint. I can always, ask a leading Socratic question that maybe you'll be able to answer, and then in the process answer your own question. I think that if you're stuck on something, then I probably have a pretty good idea of what it is. There's a couple problems in this exam that have some little tricks. I tried to make them not terrible tricks, but if you happen to not be seeing it, don't just stay up all night or beat your head against the wall or give up on the class. Send me an email and I bet I could ask you a very simple question that'll make you go like, oh, I know how to do it. So, take advantage of it. Anyways, tonight we're talking about conformal mappings. That is, we're finally going to get into chapter 5. Chapter 5, we are a ways through this textbook and we are almost at the end of the semester, which is crazy. So, conformal mappings. This is something we talked about in section 1.5, 1.3? Yeah, 1.5. So I'm going to actually just bring up this piece right here from way back. Now, conformal mappings, when we first talked about them, we talked about them just around the time we were talking about the Cauchy-Riemann equations. In fact, we actually hadn't even talked about the Cauchy-Riemann equations when we first described conformal mapping. So this is a blast from the past. If you don't remember what we were doing, the whole business of conformal mappings was all about how a map can, the definition was right here. It says you have a map from A to C. It's conformal at Z0 if there is an angle theta and a r greater than 0, such that if you have any curve gamma that's differentiable at t equals 0 and for which gamma of t is in A and gamma of 0 is Z0 that satisfies gamma prime of 0 is non-zero, then the curve sigma of t, which is f of gamma of t, this guy is differentiable at t0, and setting u equal to sigma prime of 0 and v equal to gamma prime of 0, then the modulus of u is just r times the modulus of v, and the argument of u is just the argument of v plus theta, of course mod 2. So all this meant is that if you have 2 different curves, oh, my headphones are freaking out on me. There we go. Weird. If you have 2 different curves, then the angle between the curves, as measured from like their tangent vectors, right? Under the conformal mapping, this angle stays essentially the same, right? And maybe things get like the tangent vectors maybe get stretched out, but they don't get like reversed or anything like that. They just get stretched and maybe moved, like rotated. So it's this picture right here. Now, you don't have to remember this too much because the easy way to think of it is basically that, like, if you take some sort of like a mesh or something, or, any sort of collection of paths, right? any kind of mesh really, then when you map it through under some conformal map F, notice that like, you know, you've got like nice right angles right here between these guys, right? Well, these guys here still essentially have right angles, as do these guys, right? Even though everything's all curvy, you still basically get right angles. That is, the tangent lines to these curves intersect at right angles. So it's something like that. The idea that you want to think of in your head when you think of a conformal map is basically this kind of a picture. Like, it's like taking like a rigid, like a window screen and like twisting it or something, you know? That's kind of the idea of it. Now, this is a little bit of a refresher, but let's get into it. So, conformal mappings, conformal transformations. The basic definition, this back from 1.5, we just looked at it, and the short of it is that a mapping F is conformal if for every z0 in its domain, F rotates tangent vectors to curves through z0 by a definite angle theta and stretches them by a definite factor r. Okay, so that's just saying that like you've got, you know, curve 1 and you know, curve, let me switch to a different color, curve 2, and you look at their tangent vectors, or, you know, like, okay, I'm gonna draw like some tangent lines or something, right there, and then this guy's got one, oh, like right here, right? So I'm not even gonna bother with the R piece, but basically just think about like, you've got some angle between these guys as you go in. So this one here, and then this one's going down. And so you've got like an angle like that, right? This theta. When you map this, all we're gonna actually be doing at the end of the day, all that happens when a map sends this guy through, like a conformal map, all it does, rotates it and like stretches it, maybe like a weird stretch like this, right? Like stretches it and like rotates it. See what I'm saying? So it stretches it and rotates it. So I should even be clear. The stretch is just like this. Like I haven't locked the aspect ratio, so it is maybe like, you know, getting squished, but it should be like a square. Like it just like, you know, 4 times bigger, you know, 1 over pi times bigger or smaller, right? Just doing it like that and then rotating. So that's what conformal maps do. So I've now obviously gotten this all over everything. Whatever. All right, there we go. So unselect that. There we go. So that's conformal mappings. Now we did prove this a little while ago back in section 1.5. This was a good theorem. Theorem 5.1.1, we'll call it the conformal mapping theorem, says, and this is going to be an important one, because we'll just use it a lot, and it tells us the right way to think about conformal maps in terms of how you'll actually do things. So if f from a to b is analytic, and f prime of z0 is non-zero for each z0 in a, then f is conformal. Okay, and in fact, it turns out to be the case. This is an exercise that I didn't assign you guys to be nice. If f merely preserves angles, and if certain regularity conditions hold, then f must in fact be analytic and it must have non-zero derivative. So for all intents and purposes, as far as we'll look at things, conformal just means analytic with non-zero derivative. Now I know that some differential geometers may have a little bit of beef with this definition, but it's the one your textbook uses and it's how we'll go with it. This is normally how we do this in complex analysis. Some people who do slightly different things maybe have a little bit more permissible version of conformal mappings where you can not only be holomorphic, but you could be anti-holomorphic as well, which analytic, or, you know, like analytic with respect to z bar as a variable. But we're not going to do that. We're not going to do any of that mess. Conformal just means, as far as you're concerned, ever need to care in this class, analytic with a non-zero derivative. So, an example. Let's let A be the complex numbers which have a real part greater than 0 and an imaginary part greater than 0. Okay, so what does this look like in the plane? Well, so if a, okay, so you've got real part greater than 0, that's above the axis, or x-axis basically. Imaginary part greater than 0 above the x-axis, real part greater than 0 to the right of the y-axis. So it's like this, like upper quadrant, right? Okay, and then b, we're going to take those to be the complex numbers with the imaginary part greater than 0. Okay, so in this case, b, oops, is just the entire upper half plane, right? Okay, so that's a and that's b. Then the map from a to b defined by z maps to z squared is conformal, right? Okay, and these are not including the axes, right? These are strict inequalities. All right, good. So this is sending things that have, you know, like a real, or positive, real, and imaginary part, obviously, to things that just have a positive imaginary part, because you could square, say, for example, I, which is sitting right up there in the beginning of that right top quadrant, sends it to, you know, what, like a, oh, sorry, it's sitting right here. It sends it on over. Sorry, I should say like 1 plus I. It would flip it over to a different side. So this guy is analytic, though. Z maps z squared is analytic and has a non-zero derivative, since f prime of z naught is 2z naught. And if we are throwing in only things over here, put in a z naught, 2 times that, definitely still gonna be non-zero. Now, if f prime of z naught is 0, which it's not on this domain, but if you did a different domain, then maybe, angles, in fact, don't need to be preserved. So for instance, this exact map, the x and y axes intersect at an angle of pi over 2, but the images intersect at an angle of pi. So think about how, basically just right up here, you've got these two guys like this. Now, anything that's purely imaginary, if you square it, it becomes real, right? And if you square a real thing, right, then it becomes, well, real and positive, right? So here's over there, and we get an angle of pi, right? Like a full, like flat, or drawing a terrible curve right there. See what I'm saying? Like that's pi. So they intersect at an angle of pi, yeah? All right, all the same. So a point where f prime z is 0 for an analytic function f, this is a singular point. And the behavior of an analytic function at a singular point can be much more complicated than the behavior of f near a non-singular point. So near a non-singular point, an analytic function is a conformal map. All it does is exactly what we were drawing up here. It just rotates things and stretches them. The simplest kind of transformation you can really even imagine. It's just very, very straightforward. However, at near singular points, things can be more complicated. Don't worry, we're not talking about that yet. If we went further in this class, if the semester was longer, we could get to the point where we talk about that later on in the textbook. But all we're talking about is the easy case, where we are, and I'm going to say this a bunch of different times, analytic with a non-zero derivative. So, analytic with a non-zero derivative. What does this give us? It gives us a lot. It is a pretty amazing amount of nice stuff you can get out of conformal mappings. So let's do proposition 5.1.2. If f from a to b is conformal and bijective, that is if it's 1-to-1 and onto, if every input has a unique output and every possible output gets hit by some input, then f inverse from b to a is also conformal. Okay, so conformal maps that are bijections have conformal inverses. If f from a to b and g from b to c are conformal and bijective, then g composed with f from a to c, that is, you go from a to b and then use g to take you from b to c, this composition from a to c is also conformal and bijective. The proofs of these are straightforward. So, part 1, since f is bijective, the mapping f inverse exists by the inverse function theorem. F inverse is analytic, and the inverse is given by 1 over the derivative of f. Okay, so if f is conformal, it's analytic with a non-zero derivative, so 1 over non-zero, non-zero. And so the inverse function has a non-zero derivative and is analytic and hence conformal. Okay, cool. Second one, so this is just chain rule, right? So G composed with F is bijective and analytic, obviously, since F and G are both bijective and analytic. Okay. In fact, you can compute the inverse. The inverse of G composed with F is F inverse composed with G inverse, right? Inverse, that's that. Okay, all good. So the derivative of GF composed with F at Z is G prime F of Z times F prime of Z. That's obviously going to be non-zero because, well, G and F are both conformal, so that's analytic with a non-zero derivative. Here is a derivative of G, here's a derivative of F. You're multiplying them together, they're both non-zero. You're not going to get zero out. So G composed with F is analytic and has a non-zero derivative, hence it's conformal. Ah, easy. Okay. So what you might say is that the bijective conformal transformations form a group. If you're familiar with some group theory, a little bit of abstract algebra, then you might immediately notice that that's what this is saying. However, we are not doing any abstract algebra right now, so if those terms mean nothing to you, then don't worry, that's fine. Take an algebra class. So theorem 5.1.4, the Riemann mapping theorem, is a little bit less about just how conformality is preserved. Bijectivity and conformality together are preserved under inversion and composition. And this is a little bit about what kind of conformal maps there are and when you can find conformal maps between certain subsets. So if A is this is called the Riemann mapping theorem, and it's a big deal theorem, although it is, as you will soon see, non-constructive, though still useful and interesting. So if A is a connected, and in fact simply connected region, so you need both, other than the whole complex plane, that's a piece that matters here, because it's easy to forget that piece and make assumptions you shouldn't. So take A, connected, simply connected, not the entire plane. Then what we get is that there exists a bijective conformal map, F from A to D, where D is the open unit disk. That's nuts, right? It means that, hey, pick some connected, simply connected region. It can be like a freaking nutso region. And this doesn't look that nutso, right? Okay, you got all the stuff in here, right? Okay, all this stuff. There's a map that sends this whole thing into the disk centered at 0. It's the open disk. It's only the stuff in there, right? There always is. And in fact, it does it bijectively and conformally. That's nuts. You might go, oh, well, whatever. Obviously, I could just sort of like stretch the boundary out all nice and sort of like, make this look like a circle. And then I could imagine like shrinking it down. It seems fine, right? But what are we doing when we're like stretching the boundary out all nice to make it into a circle? Well, we're like rotating angles of curves, right? Oh. And what are we doing when we're shrinking it down or like expanding it out? We're doing dilations, right? Oh my God, that's a conformal mapping, right? Crazy. Okay. So, and this is the extra crazy part. For any fixed z0 in A, you can always find some f such that f of z0 is equal to 0 and the derivative of f at z0 is greater than 0. And with such a specification, f is unique. Wait a second. This is even crazier than what we just said, because now you could pick any point here, z0, that gets mapped to the exact center of the disk. Not only that, now of course, if f is going to be conformal, a bijective conformal map f, then of course its derivative has to be non-zero. but I can explicitly choose it so that the derivative at z0 is positive, and as long as I choose it with the derivative being positive, then in that case, it is unique. Oh my god. Whoa. So this is the piece that makes that, essentially being able to put a point to that point maybe doesn't seem crazy. You just take this piece here to make it, to do that uniquely, right? Because essentially, being non-zero means that you've sort of split your derivative, if you want to think of it like this, into, you should be careful because you have to remember that f is not a real valued function, right? So it's not like it's splitting into like a positive and a negative chunk so much, right? But essentially you can think sort of that intuition as carrying over. You should be careful not to, this is fine. We'll talk about this more, about what this does, but this tells you something about, because normally if you saw something like this, you might go like, hey, wait a second, there's not a nice ordering on the complex plane. Why am I saying something is greater than 0? Maybe for now what we should say is we should say not equal to 0, though it turns out to be the case that that is still a correct statement. We'll get to that pretty soon. But for right now, we'll say something like that. Like that's fine. Essentially though, it turns out that you could maybe get 2, and the specification that thing's the greater than 0 one turns out to, give you uniqueness. Now, all the same, let's move on from that point and just kind of focus again on how cool and crazy this result is. The Riemann mapping theorem is kind of neat because it says, hey, if you've got a simply connected region in the complex plane that isn't the entire thing, then you have the disk, whatever. You got a bijective conformal map. Oh, what? That's crazy. That's nuts. Basically, it means that, hey, every simply connected region is just like a homeomorphism of the disk, and it's not only just homeomorphic, it's like conformally homeomorphic. And in fact, we should get some kind of a notion for that. Let's talk about that. So if A and B are any two simply connected regions with A and B both not equal to the complex plane, okay, then there's a bijective conformal map from A to B. Indeed, if you go from A to D and H from B to D, then you could set G equal to H inverse F. That is, since A and B, two different chunks, each have something taking them over into the complex, or into the disk, and since this is bijective, well, and since bijective conformal maps, as we talked about up here, in fact proved, have conformal inverses, we can get the conformal inverse of H, which is H inverse, the inverse, which is just automatically conformal. I shouldn't say conformal inverse, like that's some kind of a different thing, but the inverse, which is conformal, which goes right back the other way. And so I could just follow F from A, and then I could follow H inverse up to B. And notice this gives me a map G in terms of doing F first, then H inverse, right? So H inverse composed with F. Oh, shoom, shoom. There we go. Nice. So we'll call regions like this A and B, we'll call them conformally equivalent. So that is if there is a bijective conformal map from A to B. Okay. This is neat. It says that the Riemann mapping theorem is more shortly, you could say, the Riemann mapping theorem just says that two simply connected regions that are not C are conformally equivalent. There is a single equivalence class of simply connected regions that aren't C itself. Now remember that to be a region, we're non-empty. So basically we're saying, hey, as long as you're not empty or the entire complex plane, if you're simply connected regions, then you're, boom, good to go. You're the same up to conformal, as far as conformal bijections are concerned. You could just relabel everything and you don't lose the angles between curves even when you go from one to the other. All right, it's kind of cool. Now, another useful fact about conformal maps is that if A and B are two connected regions with boundaries, boundary of A and boundary of B, we're going to write that as BDA and BDB. So that is, if you've got A and B, I'm going to even stick with this. Here's A and here's like B. I'm going to kind of put like little curves around these guys. So there's their boundaries. Really, I should be drawing things like this all the time, so it's like clear that I'm like not taking the boundaries and all that. But you know, when in the stuff I did up here earlier where I was drawing pictures involving this, but you guys get the idea. So here, if this is A and this is B, then this part right here is the boundary of A, and this part right here is the boundary of B. Okay, then if F from A to F of A is conformal, so something sending A to its image, if this is a conformal map, okay, now here's what we get. If F of A has a boundary of B, and if for some Z naught in A, F of Z naught is in B, then F of A is equal to B. What? Okay, so if F sends, let me put a different color. If F sends this boundary to that boundary and sends 1 point to something over here, then it sends the entire thing to the other thing. That's nuts. That's crazy. But it's also kind of an obvious consequence of this uniqueness piece right here that you get. Okay, so we'll talk about this a little bit more. But it's really nice because it says that for conformal maps, to show that they have exactly the same image, then we need to only check that they map the boundaries to the same thing, maps the boundary to the right thing, and a single point inside, 1 point inside, and then the boundary. Can you imagine why this might be useful with things that we've done, you know, saying like on and inside a closed curve, you know, a closed curve containing 1 point. This is sort of a theme of the class. It's something about like a curve and then a single point inside, you know, those two pieces together are really giving us a lot of what we get here. And it's still carrying through in the case of conformal maps. All right, cool. So let's kind of keep this going a little bit and talk a little bit about the behavior on the boundary. So since we only need to check that a conformal map, or if we want to show that a conformal map has a given image, right? You know, that F of A is equal to B, right? If we want to see that that's true, all we need to show is that F sends the boundary of A to the boundary of B, and that it sends a single point inside to the other set, the interior of the other set. Okay, so, and I should be careful actually to make it clear here. If F of A has boundary of B, when I say F sends the boundary of A to the boundary of B, right? What I'm trying to say is that if the image of F has the same boundary as B, right? Because A and B may not, you know, they if they're open, they don't contain their boundaries, right? So we're saying, oh, if F sends the boundary of A to the boundary of B, what I mean by that is if F sends A to a set whose boundary is the same as the boundary of B, in case that's not clear. But you can essentially think of it as sending boundary to boundary for all intents and purposes. Now, the behavior at the boundary, though, is kind of an interesting thing to ask about, because obviously this is this plus checking 1 point is enough to tell you the behavior of a conformal map on an entire region, which is crazy. So the Riemann mapping theorem and most of our other remarks about conformal maps are about the behavior on regions that are open connected sets. Okay. In particular, the Riemann mapping theorem does not say what happens on the boundary of A or on the boundary of the disk. Many applications involving conformal mappings in physics and engineering, these guys often involve determining the behavior inside a region from information on the boundary. So this is going to be useful if you take certain other classes. You will see this come up again. In 5.2, we'll look at a lot of different examples involving regions such as disks, half planes, quarter planes, and so on. And the maps will be well behaved on the boundary, but it's not automatically the case that everything turns out that way, though it in fact does. So the theorem here is the Osgood-Carathéodory theorem, theorem 5.1.5. If A1 and A2 are bounded, simply connected regions whose boundaries, let's call it gamma 1 and gamma 2, are simple, continuous, closed curves, then I'm going to highlight this in a different color. Any conformal map of A1 one-to-one onto A2 can be extended to a continuous map of A1 union gamma 1, which is one-to-one and onto A2 union gamma 2. Okay, so what this is saying is that once the boundaries are known to be mapped continuously, here, let me just draw the picture essentially. This will be easier to say. If A1 and A2 are bounded, simply connected regions with boundaries gamma 1 and gamma 2, and those guys are simple, continuous, closed curve, then any conformal map of A1 that's one-to-one and onto A2. So this is a bijective conformal map from A1 to A2. You can always extend it to a continuous map on the closure of A1 that's bijective and conformal, or that's bijective at least. I'll say that's continuous and bijective, since we're not necessarily saying conformal yet, in this theorem at least. So onto the closure of A2. That is, if gamma 1 is the boundary, right, then A1 union gamma 1, this is A1 union boundary of A1, and that's just the closure of A1. So this is like if you take, the open unit disk and you close it, you get all the limit points, right? Some people, we might have written the closure instead of with that over line, we might have written it as like CL. I don't remember what we wrote it as earlier. Probably CL of A1. So the closure. Okay. So basically this is saying that, hey, conformal maps, bijective conformal maps on bounded, simply connected regions with nice boundaries extend to bijective continuous maps on their closures. So this is kind of nice. Basically it says that our previous, what I was saying and kind of drawing this extra distinction, saying like, oh, well, really we're mapping A to some subset F of A, whose boundary we're saying is going to be equal to boundary of B or something, right? Really, we didn't, what I'm saying is that's really, well, it's technically correct with how we've been saying things. Truly, it's not necessary, because in this situation, you just immediately end up with an extension of F that maps the boundary of A to the boundary of B. So really, that is exactly how you can think of it. All right, thanks to the Osgood-Carathéodory theorem. And notice, this is really actually valid for some pretty dang crazy regions. So simple continuous closed curve doesn't sound that wild, but you can come up with some pretty crazy simple continuous closed curves, and all you need is bounded regions. And this tells you that there is an extension of that you can extend a conformal map in a nice one-to-one and onto way between the closures, even if one of them is simple like the disk and the other one is just nuts. It's just crazy, you can still do it. Cool. So once the boundaries are known to be mapped continuously at least, we can get information about the regions themselves. The next theorem outlines such a procedure. Now, why this might be important is because a lot of the times in practical applications, or at least why this is important in practical applications, it's important just for purely theoretical reasons on its own. But why it's interesting in practice is because a lot of the time you only have information about, say, like the boundary of something, right? So, for example, I don't know. This is a slightly more confusing example than what you might we might be dealing with, or want to deal with. But say something like just for an example of only having information about the boundary. Say you've got some kind of a weird shape, and it's like being heated or something, right? And you only know how hot it is on the outside. Could you figure out how hot it is at a random point on the inside? Right? Something like that. Or maybe you've got like I don't know, like a yeah, something like that with like, maybe you've got like a weird transistor with like a certain shape, or I don't know, some like chip design or something. Can you figure out just from how hot it is, like on the boundary, the edges, how hot it is inside, stuff like that? So this sort of thing comes up in plenty of practical purposes. Now, this next theorem gives you the start of how we can actually do this sort of stuff. And it gives you a procedure for finding more about the regions themselves from information about boundaries being mapped continuously to each other. And the conditions we're going to use are in fact restrictive enough that we no longer need to check a point z naught in A to use this. So this is kind of cool. All right, so theorem 5.1.6, if A is a bounded region with f a map from A to C, a bijective conformal map onto its image f of A. Obviously, if it's bijective, it's onto. So it's we should, I wish they didn't write this. We should really say A to f of A, right? Okay. Suppose that f extends to be continuous on the closure of A, and the f maps the boundary of A onto a circle of radius r. So in reality, we should just say, what they're trying to say right here is that f sends A into, like, it takes values in the complex plane, but we're trying to really say that f goes from A to B, and that B is actually a circle of radius r, right? The open disk of radius r or something, right? An open disk of radius r, because otherwise, if it, we're saying it's bijective, so if in case that's confusing to anybody. So extends to be continuous on the closure, and the boundary of A maps onto a circle of radius r, then f of A equals the inside of that circle. More generally, if B is any bounded region that, together with its boundary, can be mapped conformally onto the unit disk and its boundary, and if f maps the boundary of A onto the boundary of B, then f of A equals B. So the reason they put the C here is because they didn't want to give away the conclusion that f of A is equal to that, but we should just put f of A right here. And it's a bijective conformal map into its image. What we're saying right here is basically that, hey, if I can extend f to be continuous on the closure of A, then if f maps the boundary onto a circle of radius r, f of the interior of that boundary equals the interior of that circle. And indeed, if you replace circle with some other set, if you say, hey, if f maps the boundary of A onto the boundary of some set, then f maps the interior of A onto the interior of that set. That's cool. That is pretty sweet, actually. That is pretty wild. So let's prove this guy. So if we compose f with the conformal map H that takes B to the unit disk, then it's sufficient to consider the special case in which B equals the disk D such that modulus of Z is less than 1. That is, if we just go right back to what we were saying here about going, from here to here to here, instead we could just go from here to here. This is all we're doing now. So it's enough to look at the case where B is equal to the disk, since we could always go from the disk to B, right? If B satisfies this stuff. So if B is a bounded region that together with its boundary can be mapped conformally onto the unit disk, then you can map it from the disk to the other direction too as well, right? That's what we were saying. Since conformal bijective maps have bijective conformal inverses, so we'll just look at maps to the disk, since we automatically know that anything that we can get to from the disk, well, if we can get to the disk, then we can get to anything that we can that goes to the disk by just going backwards, right? So on the boundary of A, the modulus f of z will be 1. Why? Oh, I think I've almost gone over. Why will this be the case? Did I miss a theorem in here? I hope I didn't miss a theorem. And make sure I didn't miss a theorem that I wanted to use. No, I've missed it. Well, then this is a... You know what? I will leave this proof for next time. We'll go back over this guy with a better picture next time, because I left off a piece here that I wanted to put on. So we will do the rest of this proof on Wednesday. We're actually running slightly ahead, and I shouldn't have made this as long of a class as I did, given that everyone's working on an exam anyway. So let's call it for tonight. We'll pick back up actually tomorrow, I suppose, since I'm recording Monday, Tuesday, Wednesday instead of Monday, Wednesday, Friday this week. So we'll pick back up tomorrow. We'll get a little bit more. We'll finish this out. We'll do a few. We'll look at a few more cases. Then we'll get into the next section, which has a lot more interesting examples, since I'm sure that will help make this a little bit less confusing once you actually start to see some specific regions mapped to other things in nice ways. So let's call it. Good luck on your exam. Send me an email if you have any questions, and see ya. Have a good night.